So this is this is problem 2.23 for standard 2.3. So the first part, the whole question, it gives you these two operators. A is this matrix, B corresponds to this matrix. Part A of the question asks if the operators A and B commute. So in other words, does A times B equal B times A? Or, rewriting it, A times B minus B times A would be 0 if they commute. And so first I found A times B, which is this matrix, and then I found B times A, which is this matrix. And if we look at them, well, they have non-zeros in the same positions. They have different inputs at two of these spots. So here it's A3, B2, and A2, B2, but down here it's A2, B2 down here, and A3, B2 here. So the only way that A times B could equal B times A was if A3 equals A2. In other words, they do not commute. So part B asks to find the eigenvalues and the normalized eigenvectors for each of the operators. So A is already diagonalized, so we don't even have to do any work for that. So the eigenvalues are just A1, A2, and A3. And then the normalized eigenvectors are these three, and they correspond. So this one goes with A1, this one goes with A2, and this one goes with A3. And then for B, I got lazy and I used Mathematica to find the eigenvalues and eigenvectors. So I plugged in my matrix here, and A is actually B1, and then the B's are B2. And then, so when you plug it in, you can just tell Mathematica eigensystem, and that gives you the eigenvalues and their corresponding eigenvectors. However, these eigenvectors are not normalized. So here are the eigenvalues it gives, which are B1, B2, and minus B2. And the eigenvectors that correspond to them are right here. And then, so we have to normalize them. So the first one, it's 1 over the square root of 1 squared plus 0 squared plus 0 squared, which is just 1 over 1. So this is its normalization, and it's just times 1. For this one, it's 1 over the square root of 1 squared plus 1 squared, which is just square root of 2. Same thing here. So these are the normalized eigenvectors, and this one corresponds to B1, this one corresponds to plus B2, and this one corresponds to minus B2. And so part C asks to find the possible results of a measurement in state 2. And so in state 2, it can either be B2 or minus B2. And so we are left with this. So in state 2, it is 1 over square root of 2 times ket B2 plus 1 over square root of 2 minus B2. And then, so for the probability of B2, it's just 1 over square root of 2 squared, so we get 1/2. And then for the probability of minus B2, we get 1 over square root of 2, which is just 1/2. And then it asks the same for operator A. So instead of, we would do the same thing, but instead of B2 and minus B2, we would have A2 and A3, and then we just get the same things again. So the probability of A2 is 1 over 2, and the probability of A3 is 1 over 2 also. And so part D asks how A and C are related. And so these parts are showing us that if we take a measurement of, in one and of like, say like S of X, S of Y, or S of Z, and then we go to the next state and we take a measurement in the other, in one of the other two, we would actually lose the measurements from the previous part that we took. So like a simple example of that would be, like, say we had a half spin system, so it can either be, the spin can either be plus or minus, and say we take a measurement of the plus spin of like 200, or we get 200 particles that have a plus spin, and then we take a measurement of those plus spins, but now instead of S of Z, we're doing S of Y, and so now we're measuring the plus spins of those 200 but now in S of Y, so the probability would be 100. And then so now we're going to do a third measurement, but again, like the first, we're going to measure the spin probability in S of Z again. Now you would expect all of the particles to be, so all 100 of the remaining particles from the plus in the SY that we just did to be positive in the SZ, since that was the first measurement we took. But the second measurement cancels out, or doesn't cancel. We lose the measurement we took in the first place. So instead of all 100 being plus spin in the SZ, actually only half are plus spin in the SZ. And so this is that's just an example of how we would lose measurements